If I were to ask you what the square root of 9 was, what would you say? Well, lots of people know that the square root of 9 equals 3. Okay, and if I were to ask you, like, mathematically why the square root of 9 is equal to 3, what does that even mean? Well, most people would say 3 times 3 equals 9, right? And that's correct. But in this video, I'm going to dive into more like what radicals actually are, what's going on in this operation, the square root, to give us the number 3. What does it even mean? So let's take a look at the kind of classic example, the square root of some number. Let's call it a. Okay, so whenever we're square rooting something, there's an imaginary 2 here. So if there's no number there, we're going to assume it's a 2. Okay, and if there's no number on the exponent of a, we're going to assume it's 1. So the square root of a can be written like this. These are the same thing, except it's common knowledge that if there's no number in the square root, this part here is called the index. The index is 2 if nothing's written, and the exponent, right, the power that a is being raised to, is 1 if there's nothing written there either. So if we were to write the square root of a as an exponent, a is our base of the exponent. The exponent that the a is being raised to inside the radical, the part inside the radical is called the radicand. Okay, we take this 1, it's the top of our fraction, and we take this 2, it's the bottom of our fraction. So anytime we're square rooting a number, we can write this as an exponent as a to the power of 1 over 2. Okay, so the square root of 9, if you put that in your calculator, you could say the 9 to the power of 1/2, that's going to equal 3 either way. So if you put that in your calculator, either of these examples, you're going to get 3. Okay, so let's see here. If we had the square root of 9, I'll just keep using this example, right? I'll write 9 to the 1 here. This is a 2. So why does this actually equal 3? We kind of went over the laws, radicands, indexes, all that kind of stuff, but why does it actually equal 3? Well, 9 is the same as 3 squared, because like I said in the beginning of this video, 3 times 3 is 9. So instead of 9 to the first power, I can write this as 3 squared, right? Square rooted. And remember, if I wanted to write this as a power, as an exponent, my base is 3, right? The big number inside the radical, the radicand. The top of my fraction on the exponent is going to be the power the 3 is being raised to inside, and the bottom of my fraction is the index on the radical. So this is the same as 3 to the power of 2 over 2, right? 2 over 2 is just 1, so it's 3 to the first power, which is just 3. So you might be thinking, well, what's the point of even doing this? Like, obviously the square root of 9 is just 3. Why do we have to analyze it this way, like more mathematically, in terms of powers and indexes and fractions? Well, it's because the hardest question you're going to get on your test isn't the square root of 9. Because people know how to do that. We're going to have to use our knowledge of laws of radicals and properties of radicals and fractions and exponents and laws like that. So what radicals are doing is they're intertwined with exponents or numbers being raised to the power of fractions. So let's think of another example. Let's do I don't know, the cube root this time of 15 squared. How could we write this as a exponent? Well, if we wanted to get rid of the cube root, what we'd have to do is we take the 15 as our base, right? This big number here is always the base. The power it's being raised to is going to be the top of our fraction. The index is 3, so that's the bottom. So these are the same thing. Okay, we're going to have to remember that in the videos I'm going to do a little later here. And let's do one more here. Let's do the cube root again. Actually, no, let's do the fourth root. Let's kind of up the stakes. Let's do the fourth root of 16 here. Okay, so 16, that's the same as 16 to the power of 1. Well, If we put it in our calculator, obviously we're going to get the answer, but let's think about how we could use our knowledge of exponents and fractions and stuff to get this as an actual answer that we can kind of compute ourselves. So 16, if we split that kind of in half, we're going to get 2 times 8. Okay, if we keep going with the 8, we kind of make a factored tree, we're going to get 2 times 4. And if we split the 4 into 2, we're going to get 2 times 2. So 16 is the same as 2 times 2 times 2 times 2. Okay, so 2 times 2 times 2 times 2. So there's 4 2's in here. So 16 is the same as 2 to the power of 4. Well, let's convert this to an exponent and see if we can make any sense of it. So 2 is our base of the exponent. Remember the big number in the radicand. The power that the 2 is being raised to, right, as the exponent is the top of our fraction, and the index is the bottom. So it's 2 to the power of 4 over 4, right? So this is 2 to the power of 1, which is just 2. Okay, what if this was 2 to the 8th power in here? Okay, what if we weren't dealing with 16? We were dealing with some big number, 2 to the 8th, which is like 256 or something. So the fourth root of that as an exponent is just 2 to the power of 8 over 4. Well, 8 over 4 is just 2, so that's just 2 squared, which is 4. So the fourth root of 2 to the 8th, whatever that is just 4. So if we can get it into this form and then change it into exponential form, or exponent form, it's going to be a lot easier to analyze these radicals. So that's really what radicals are. That's the operation kind of behind the square root and the cube root, all those kind of weird symbols. So this is kind of the basis of what we need to know. And in this whole series, in the whole playlist, we're going to be going over how to really break down radicals into equations and even graphs. Okay, so I hope this is helpful, and I look forward to seeing you for the rest of this series.